Hello everyone, welcome to yet another video series of electromagnetic fields. I'm very happy to look forward for you in this video because through this video we are uh, discussing a lot of interesting topics with respect to electromagnetic fields. So in today's video we are starting a new unit, which is magnetostatics, wherein which we are going to discuss about the basics law governing magnetostatics. So let's recall the previous topics. So in the previous unit we have discussed about electrostatics, wherein which we first dealt about the fundamentals law, and then we have discussed what is meant by electric field intensity, flux density, what is electric potential, and what are the boundary conditions for conductors and dielectrics, and at last we discussed about capacitance and electrical energy, capacitance and energy density equations and its applications. So in this video series we are going to discuss about magnetostatics, wherein which we are going to first look for the fundamental laws that governs magnetostatics. So we have three basic laws: Lorentz law of force, Biot-Savart law, and then Ampere's circuit law, just as we have for electrostatics. So these are the major governing laws for magnetostatics. So first in this video we are going to see about Lorentz law of force. This is the agenda. First we have a force demonstration, and then we'll be discussing about the Lorentz force equation, and then how we going to sketch this Lorentz force, and then how we can practice using a right hand rule, and then we have a short squishing session also. First, let's explore the magnetic force in action. Now you can take this image and you can make your own live demonstration for magnetic force. Have a simple circuit setup wherein which a wire is placed within a strong magnetic field. So when we pass an electric current through the wire, we will be noticing a distinct movement, right? Why the wire moves? When you are having a strong magnetic field and we are placing a current there, current carrying conductor or wire, the wire moves when we supply it. Why? This demonstration of a current carrying conductor placed in a magnetic field is a good example of the microscopic Lorentz force. Yes, the movement of the entire wire is a cumulative result of the magnetic force acting on each individual charge carrier inside it. So, what is that Lorentz force which is responsible for this wire to move? Let's get into it in detail. The magnetic force on a single moving charged particle in a magnetic field is described by using Lorentz force equations. Lorentz force is a microscopic force, magnetic force exerted between the charge carriers when we apply current to pass through it. So this force can be mathematically expressed as F is equal to Q into V cross B, where F is the magnetic force vector and Q is the charge of the particle and V is the velocity of the vector particle, and then B is the magnetic field vector. Here the symbol X is a cross product, which means that the force is always perpendicular to both the velocity of the charge and the magnetic field. And the magnitude of this force is given by F is equal to QVB sine theta, where this theta represents the angle between the velocity and flux density. Now we are here to visualize this vectors using a electromagnetic field by sketching these vectors in different scenarios. Okay, now how we can find this magnetic force, in which direct it is exhibiting? By using a right hand rule we can easily find the direction of this magnetic force. So by using the right hand rule, wherein which the thumb will point to the magnetic force and the forefinger represents the current directions, and the pointing finger represents to the direction of the magnetic field. How we can use this right hand rule in practice? By electron